Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 394. Find edges in shortest paths. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. So this one, I want to go over one thing real quick. This first part is going to be a little bit fast. My apologies. Just because this is pretty fundamental, pretty basic, so I'm not going to go over the details of Dijkstra's algorithm. Here you're trying to find the shortest path from 0 to n-1. It is a Dijkstra's algorithm problem, and I'm not going to go over the Dijkstra's part very much in detail, but I feel like one thing that I want to point out is that, and people kind of talked about this either last week or the week before, is that you have to remember to do this thing. The reason is not because it's a trick or an optimization or whatever. It is actually a very fundamental part of Dijkstra. I don't want anyone to ever write Dijkstra without this thing. And just to go over very quickly, the reason why you need this, and in the past, I think Leetcode was just sloppy with bounds, so they didn't care. But in any reasonable Dijkstra's algorithm, you need this. And the reason why you need this, and the reason why it doesn't come up on textbooks, is not because textbooks are sloppy or whatever. It's because in the textbook version, heap is updatable, right? The thing is that heap is updatable, so then when you update the costs in a heap, the heap reflects the true cost of every node after that update, right? However, if in the heaps that we use, or as I use, in standard library, there's no update function in heap, right? So what we do is instead we push another object on the heap, which is fine in a sense, but basically what that does is that it allows us to it's not quite a lazy update, but a lazy removal of, like, basically, if you think about an update as insertion and deletion, right? If you want to think about it that way, I don't know. Then now this is, you do the insertion and then the lazy deletion of that update, if that makes sense, in a non-atomic kind of way. So okay, and the reason why this is important is that because you push to the heap multiple times, so if D is greater than your best answer, that means that you already have parsed this node. And if you already parsed this node and you parse it again, then it's going to cost you more and more expensive things. And the thing with that now is that because the size of the heap is now, instead of log v being the number of vertices, is now log y, which is the number of edges, because you can kind of think about how that works. So it's log y instead of log v, which is more expensive. But if you also do the math, y in the worst case could be v squared, assuming no multiple edges, etc., right? Self edges, all these things. Roughly v squared, and log of v squared is just equal to 2 log v, which of course, if you're a big old notation, it is just going to be 2 times slower, which is fine for the most part, unless you do something really silly. Anyway, so that's Dijkstra's algorithm. I want to bring it up. Maybe I'll do a separate video, because I think last week people had a lot of craziness about it. But yeah, so then the idea here is, okay, what do we do to settle this find edges thing, right? Well, one thing you have to remember about Dijkstra's algorithm, and I kind of pointed out last week, is that it is a greedy algorithm, right? It is greedy in that the shortest path from A to C, I don't know why I say C, from A to B, if C is on the shortest path from A to B, then the path from A to C is also the shortest. Kind of this idea of like building up this optimality, right? And so, and I don't know, sometimes I think people assume that because you do it so quickly, you memorize these things and all these facts. But to be honest, I didn't. I mean, I was definitely not slow, but I also wasn't that fast, right? To be frank, I was just like thinking a little bit about just thinking about the proofs and stuff like this. But the idea here is just to calculate the previous edges that lead us to this optimal solution, right? Because as I said, because this is greedy, that means that the move that leads to this greedy move is also, because this algorithm is greedy, if the best move to this current node is optimal, that means that if something that gets me here at that time previously, that's also optimal. So basically, you build on this base of optimality and build it off. So what is interesting about this particular problem is that there may be more than one shortest path, right? We kind of mentioned this, and in example 1, you could kind of see what happened here. In example 1, you could see one idea, and another one maybe you could just see like a lot of ones. Then just kind of there's just a lot of different ways, right? But here they actually illustrate the problem pretty well, I think, and you have to see which edge gets used. Yeah, and then now, and the idea here then is that, as I said earlier, if A gets to B and B gets to C, the shortest, then, and the proof of greedy is just by contradiction, right? Because if there's another shortest path from A to B, then you would just take that path, and then now you end up with a shorter path. And I don't know. Contradiction, I guess. I don't know. Maybe that's not it. I don't know. I don't remember the proof, to be honest. But I think that's roughly right there. So then now here, in terms of what I do, is that I just keep track of all possible previous lengths, right? Because if I know that, let's say, you have a diamond-shaped thing where you go from top to bottom, and you go the same, that means that at the bottom, that means that the cost is the same on multiple paths, and the cost is the same on multiple paths. That means that the parent or the previous or the ancestor, if you want to call it that, those nodes are also optimal. So then now, because in a way, if you think about shortest path and they tie, that means that it doesn't matter which one you take, right? Each of those paths. So then now, you just try to figure out, okay, there is an optimal way to get it from this previous path. So let's keep track of it and then, keep going, right? And yeah, that's basically the idea here. I keep a list of them because there could be multiple of them for tie-breaking reasons. If we have a new best, I set it to a new list because you want to clear the old one. You just want to, set a new list with the now as in the index. Oh no, the previous node, and then the index of the edge that we kind of keep track of as we adjust it to the list. We use this index in the answer. Otherwise, if it is Leetcode, that means that we found an additional path that gets to this node. So then here we just append it to the ancestor or previous or whatever. And then here we do it's not backtrack, I don't know why I call it track, but it's just almost like a path reconstruction, right? One thing to note is that if you want to do every possible path, it is going to be exponential number of paths, and that is no bueno. But it just means that some edges can be used multiple times. And in this particular problem, we only have to care about which edge gets used possibly in one shortest path. And so that means that if we processed a node, then we're done because we already calculated all the edges that comes into it, right? So we're kind of looking at it backwards. And that's basically how we do it. We set done, we set n-1 as in the last node that we tracked from, and now we know the previous node that goes into it, right? If we already done this, we return because we already finished this node. Otherwise, we set to done. And then for each node, or for each edge that is on the previous node, we have the re, and then the index of the edge, we set it to true because that is the problem. And then we go up that node to see if it needs to be done. And that's pretty much it. The big part about this is just setting it done because we don't need to reconstruct that path. We just need to, because that means that there are multiple paths to this node, and that's fine. because we don't need to process the ancestor to this node more than once. And of course, this is a very standard depth first search if you kind of recognize it that way, even though it's written a little bit awkwardly. And of course, that's going to be v plus e, which is adverse of e time. So this is v plus e. This is Dijkstra, which is e log e, right? The way that we wrote it with the heap. This is linear, everything else, and so yeah. So this is going to be log. The complexity of this is going to be e log e plus v plus e. Well, I guess you don't need the v plus e, the e part of v plus e. You just e log e plus v, and yeah, and the space is just v plus e because we just have, we have a heap which is O of e. We have adjacency list which is also O of e. We have these O of n things actually here. Maybe not the h, but O of n things here. And this takes O of n stack space if nothing else for the nodes, but also O of e for the answer. And yeah, that's all I have for this one. Let me know what you think. Let me try to make it slightly smaller so you can maybe see most of it. I failed anyway. So here's the top. Here's the part up to the heap, right? And then here's the DFS backwards from the shortest path spanning tree. Yeah. Well, I guess it's not a spanning tree the way that I did it, but you would traverse it like a tree. But yeah. That's all I have for this one. Let me know what you think. Thanks for watching. You could watch me solve it live in the contest now. What a typo. What a typo. What a typo. Oh man. I was slow and I still made a typo. Okay. Whew. Okay, focus. Someone feel got this. You should be able to do it. That 5 minutes is stupid though. Okay. Graph and nodes. I'm tilted a little bit. Okay, focus. Okay, you have edges. Okay. Shortest path from 0 to n minus 1. You're where edges of I is at least one shortest path. What does that mean? Oh, so you're given these edges. Or the shortest path from 0 to n minus 1. Or shortest path. It should be okay. Yeah, let's convert this. I think this would have been a very good contest if I didn't just messed up that typo. Had it. Yeah, oh well. I mean, I still have time to mess this up, so. Right? Okay. Well, no, finish it out. Okay. And then now, shortest path from 0 to n minus 1. Okay, yeah. Trying to think, okay. What am I doing? We are doing texture. Okay, yeah. Zero, zero. No, that's fine. Why am I so slow? this is not quite it. What we want is if why am I struggling so much? Nope, this should be also this is wrong. Okay. Okay, it does something. How are people so fast? I mean, I guess they templated this, but still. Okay. No, I want this and index. Right. And then now n-1. Okay. Is this even right? Well, this is probably not right when it's returning just false all the time, but is the second one right, roughly? Nope. What am I doing wrong? Definitely wrong. What am I doing? Debugging is not great. Oh, we wasted 5 minutes, so this is terrible. Okay, it's not putting anything. Why? Is the other parts right? Nope. Why isn't the other parts right? I messed this up. Wow, I don't know how to. I don't know how to. Did I mess this up? Oh, what the? No, this is we. What are you doing, Larry? I am just really off today. At least that didn't cost me a wrong answer, but. This is impossible to read. Okay, I think this is good. Or at least it matches the thingy. So let's give it submit. Silly mistake on Q3. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, this problem, explanation. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye-bye.